We're going to finish this simple approximation problem. I'll just talk about it maybe for half the lecture today. Then we're going to move on to introducing polynomial spaces, talk a little bit about why they're predominant. And then I think that may take one lecture, and then I'm hoping that we'll dive into the meat of the material at the end of the week or the beginning of next week. All right, so let's just say a few concluding remarks about the Galerkin method before we move on to discretization and splines and elasticity and all that stuff. You've probably noticed that we've restricted ourselves to a very simple problem of basically fitting functions because it allows us to study the stuff that's under the covers a little bit more clearly without being, you're going to find as we introduce the physics, it can make it difficult to separate the method from the physics. And so this is an opportunity for us to just spend some time on the background underlying math. So can you guys see my screen? Am I sharing?
Yes.
Okay, great. So we're talking about the Galerkin method. And let me annotate here. So we're talking about the Galerkin method, and really the distinguishing feature here is that if you have a infinite dimensional space and you pick some finite dimensional subspace, you get kind of a natural structure for approximation. And this subspace relationship, although it seems kind of like a trivial or obvious thing to do, it actually has some, it yields some beautiful properties in the methods if they satisfy this relationship. First one I want to talk about is this idea of orthogonality. So going back to just simple R2 and R3, let me go ahead and draw again this problem we talked about before, just because it gives us kind of a concrete. Okay, so let's say the XY plane, we're going to call R2 is the XY plane. Okay. Let's say we have some vector F in R3. Let's say that it's just the vector 1, 1, 1. And let's say we're trying to find a solution, UH, in R2 that approximates F, okay? So the Galerkin structure, one of the guarantees that you'll get from this structure is that the error will be orthogonal to your discrete space. In other words, there's not going to be any component of the error in the XY plane. It's all going to be out of plane in this simple example. And that holds in general for these Galerkin methods. And so orthogonality in this case means that if you define your error, right, let's say, for example, you compute UH to be this guy, right? So UH has components in the X and Y direction. Then let me redraw that arrow. This arrow here is the error. So it would point the other way. Okay, so this guy is the error. And notice that it's pointing out of the XY plane. That's what we mean by orthogonal. So in other words, if we take the inner product for the problem that we've defined, and we take the inner product of our error with any test function, it should be 0. And what that tells you is there's no component of the error that lies in the space VH or UH in this example. Okay, so in this two-dimensional example, there's no component of the error that lies in the XY plane. And that's a guarantee that you get from Galerkin. The next big guy is what we call best approximation. And it also follows from the orthogonality requirement. So orthogonality, I won't go through this proof in detail, but orthogonality is one of the requirements in order to get best approximation. But what it says is, in fact, there is no other function UH, like there's no, let's say, big UH. If we were to pick some other big UH in our VH, there is no other guy whose error is smaller than the computed little UH. That's what we mean by best approximation. And you can kind of see in this example what that means is if we computed, like, let's say we computed some other guy, let's say this was big UH. What you notice here is that the error vector is going to have a component. Notice there's a component. See how there's a component in the XY plane? And that's not possible because of the orthogonality of the error. So it eliminates any possibility that the solution can drift off of basically of the orthogonal projection of F into the space. So that's kind of the intuition that the picture to have in your mind as to why it's the best approximation, because if you float it off of little UH in any direction, then that requires that the error have some component that's in VH, that's in the XY plane, but that's impossible because you've already proven that the error has to be orthogonal to VH. Okay, so those are kind of the two big guys, I would say, and the mathematics of finite elements is a massive, I mean, it's a massive body of literature and research, but from the standpoint of the roots of it all comes from some of these basic ideas about the Galerkin method. Okay, so let's talk just for a moment about the linear systems. So I want to introduce you to this very important result from linear algebra. It's called the rank nullity theorem. And what it says, basically, as I've written here, is if you have a linear operator, M, that goes from space V into space W, and M is finite dimensional. Okay, and because it's finite dimensional, you can think about this as if it's a matrix. Okay, so every linear transformation in finite dimensions is a matrix representation in terms of a given basis. What you can say about this operator is that the dimension, if you remember what the dimension is, like the number of basis functions. So if you look at the dimension of the image of M, right? That's like, so if you think of M as a matrix, it's going to take M, let's see, D is equal to F. Okay, so the image of M is, so D comes from V, and then M sends D into W. It's everything from V sent through M into W. That's the image, right? It's everything that it maps into W. We call that the image of M. It's a space. It's some subspace of W, and it has a dimension like any linear space. So if you can figure out the dimension of this guy, and then you add the dimension of the kernel of M, and remember the kernel is all vectors D that are mapped to 0, right? So you're taking all of the vectors in V that when you multiply them by M, it sends it to the 0 vector. That is called the kernel. And so the kernel of M is actually going to be a subspace of V. This guy is going to be a subspace of W. And so the dimensions of these two spaces has to be equal to the dimension of V itself. Okay, so let me try and reason with you for a moment about why we care about this result. Okay, so let's talk about the kernel. We've talked about this briefly. This means if you have a matrix, right, and it maps something that's non-zero to 0, what you know is that M is singular. Okay, so an analogous way to think about singularity of matrices is that they're operators that have a non-trivial kernel. So the dimension of the kernel of M would not be 0. It would be something greater than 0 in that case. Let's assume, though, that M is well posed, meaning it's not singular. So this guy here, let's say that its dimension is 0. Okay, because that's the usual case, that we're dealing with well-posed operators. We have appropriate boundary conditions. So let's assume that that guy is 0. So then that simplifies this to the dimension of the image. The dimension of the image of M is equal to the dimension of V. Okay, so let's talk about this. The dimension of V, we build V, right? V is our finite element space, right? So we're supposed to be constructing this basis for this space. So we should know the dimension of V. And so if we construct V and we construct it correctly, then we also know the dimension of the image space. Now, problems, especially with splines, is that sometimes it's hard to know what the dimension of V is. You may think that you have a basis, but maybe you don't. Now let's talk about that case for a minute. Let's say you're an analyst and you've built a spline basis and you think it's a basis, but let's say it's not. What does that imply? If the dimension of V you thought was, I don't know, 100, but it's actually 99, what does that then tell you all of a sudden? What will happen? So you're off by 1. Where does that, if you look at the rank nullity theorem, you thought this was 100, but it's actually 99. The image is 100. So what does that imply? You're
The null
actually
space is
singular.
non-trivial.
Yeah, you're going to be singular. And so this is a big deal with traditional FEA, C0 finite elements. It's very easy by construction to make sure that you have a well-formed basis for your finite element space so you can count the dimension. With smooth splines, this is a non-trivial exercise, and we spend a lot of time trying to figure out exactly whether or not we have a basis. If we get it wrong, it's a big deal, because the implications of getting this wrong is that the kernel of your operator will in fact be non-trivial and you will not have an invertible system. And so the point to make here that's very important is that with splines in particular, and we'll talk about this again and again, the properties of quote unquote the basis have a huge impact on the properties of the actual operators that you discretize M. So if you compute a basis, for example, that's linearly dependent, then when you use it to discretize an operator, you will get a non-trivial null space, and therefore you will not be invertible. It'll kill the whole simulation right at the beginning. Equivalently, if this in fact is a basis analytically, but let's say it's poorly conditioned, and we'll come back to that. I keep using that word. We'll come back and spend quite a bit of time on this. If it's poorly conditioned, then M will also be poorly conditioned for any physics you choose, right? In other words, the conditioning of the basis, if it's poor, M's conditioning will be poor independent of physics. Sometimes physics can make your operators poorly conditioned all by itself. And that's like another problem you have to think about. But if you get the basis wrong, then M is always going to give you problems no matter what you discretize. And so understanding kind of these basic relationships in the finite dimensional setting helps you kind of understand the implications for what we're doing with the discretization. And we'll for sure come back to this again and again. Okay, any questions on that? What we've covered so far before we kind of turn the page?
Mike, can you show an example of a PDE where your basis led to poor conditioning so that you couldn't do an operator?
Well, any spline basis that has a linear dependency, so it's not actually a basis, will do that. Any of them. So anytime you have a linear dependency in your set of functions that you're calling a basis, the operators that you discretize with that basis will have a non-trivial null space, and therefore they'll be singular.
Is a poorly conditioned basis always just a basis? It's not actually a basis.
Well, if it's linearly dependent, then it's not a basis. But you can have things that are analytically a basis, but to machine precision, they're not, or they're close to being linearly dependent. Then you have poor conditioning, and then your matrix will also be poorly conditioned.
Right, so earlier you mentioned like the monomials as being a poorly conditioned basis, right?
Yeah, we're gonna talk about that in a minute. That's the next topic, is looking at some of these bases now. Yep. So this is a big topic in this field, is that we can now build very sophisticated function spaces for approximation, but they're also, you have to really understand what you're doing, because you can introduce parasitic behavior in the basis, and it will manifest in the actual discretization of the physical operators. And likewise, if you get the basis right, then you can discretize a huge array of operators that maybe you couldn't do before. So it's kind of a two-edged sword. But we'll talk, we know how to do this. We know how to control this stuff. So we'll talk about how to do it.
Dr.
Okay.
Scott, could you go over what this image of M is again? I didn't quite understand that part, or could you maybe show an example of that?
Right, let's see. Okay, let's take a look at a matrix. Let's say we have a matrix that is, let's see, A11, A12, A13, A21, A23, A31, A33. Okay, let's say that's our M. Okay, let's view these columns as little vectors, okay? These are each vectors, okay? So let's call this A1. The first column we'll call A1. Call the second column A2. The third column A3. Then we can rewrite this matrix now as A1, A2, A3. Okay. So what is the image of M? The image of M is any linear combination where you can take like, let's see, so you're going to multiply this by C1, C2, C3. Okay. So this is equivalent to the inner product of these vectors, these column vectors with C1, C2, C3. And so the image of this operator M is any vector that can be represented as a linear combination of the columns of M. Do you see that? You see how this is actually A1, A2, and A3, they're acting like basis vectors. Do you see that? And then C1, C2, C3 are the unknown coefficients. So the image space is any vector that you can get to using this combination, right? Any coefficient C1, C2, C3 times the basis vectors A1, A2, A3, which are actually the columns of M, this spans the image space of M. So this is a very instructive way to look at a matrix. In other words, what we're saying is that the columns of M actually create a subspace of R3, don't they? Right? You see how they're length 3? So these are actually, if the columns are linearly independent, then the columns of M span R3. And so the image space of M would be any vector that you could generate from the columns of M. So I don't know if that was helpful, but
No, that was very helpful. Thank you.
yeah, it's nice to view a matrix as just an inner product, because then you can see the structure, that it's nothing more than basically the columns are a new basis, and you just take each of those basis vectors and multiply them by the coefficients, and that generates the image space. It's every possible vector of that form is the image space. And so you can see right away that if you have a malformed basis, what's going to happen is that one of these column vectors, or some combination thereof, are going to be linearly dependent on the others. And so you'll actually get a linear dependency in the column space, which just means these columns are there's some linear dependency amongst the columns. And that comes from the basis, because this is nothing more than the coefficients of the operator with respect to the basis that you've chosen. So you can see that you can screw up your column space if you don't have a good basis for your finite element space.
Dr. Scott, I had a question regarding that theorem that you stated with the dimensionality.
Mm-hmm.
I was wondering, you had mentioned that you can kind of determine if matrix M is ill-conditioned based on this theorem, and I was wondering if in within codes or within software like Abacus or whatnot, if they have certain checks in the code using this theorem, or if it's practical to write that in the code base.
So yeah, I can answer that. Generally speaking, before you start using a new finite element basis, you should be sure that it's a basis. It's not an acceptable practice in finite elements in industry or academia to run with bases that are not bases. So if that happens, that's just bad work by the people that develop the technology. So we try and eliminate that possibility a priori from the issue, from the possible sources of error. So like an abacus, you're never gonna use a space that has a degenerate basis. That's rarely, if ever, done. And if it is done, it's eliminated before it gets to the assembly of the linear operators. So if that's eliminated, if you have a degenerate column space, that they do look at the column space of the matrices and compute, for example, if the matrix is degenerate, because that will help you know maybe you don't have the right boundary conditions or something, right? If you have a, because you know, if you look at the rank nullity theorem, if you can count, if you know the dimension of V, let's say it's 100 or something, right? And you thought that your null space was 0, let's say you thought it was 0, but what you're finding is that when you look at the column space of your operator, let's say it comes out to be 99, then you know, oh, this has to be 1. So I know that I'm non-singular, which means there's something wrong with M. And so usually if your basis is good, if this is okay, then, but you have an unexpected kernel, it's almost always boundary conditions. So if you don't apply boundary conditions to a problem, for example, correctly, then you may have a non-trivial kernel, like rigid body modes, for example, and that will disrupt your linear operator M. So that's how that, so some codes will help you, you know, like they'll, especially a lot of the structural codes, they may help you try and figure out if maybe you don't have a boundary condition correctly set, right? They'll look at the operator and try and help you see that. But in general, it's expensive, right, to do that. So these are expensive computations to back out these properties. Did I answer your question at all, or?
I was just wondering if the code specifically called out this algorithm, but I think you said it was expensive to calculate. So I imagine there are other catches.
Yeah, I mean, to really analyze a linear transformation, normally you do what's called a singular value decomposition. And that's maybe even more expensive than the finite element calculation itself. And so that's why we try and make sure through proving theorems or whatever else we may need to do that we've got a hold of this. Because once you get a hold of this, then it's just, is my problem well posed? And if it is, then you're going to know that so if you know you have a basis, then you've got a handle on the right-hand side. If you know your problem is well posed, then you know this is 0. Right? And so then you know exactly what the dimension of the image space should be for your problem. So that's the best way to work.
I have a quick question.
Okay.
So you alluded to this. So for any two-dimensional mechanics problem, before you apply boundary conditions, you're going to have a kernel space of 3, right?
That's correct.
Regardless of whether your basis is,
That's
I mean,
correct.
that's when you have a correct, a proper basis.
That's exactly right.
Yeah.
That's
okay.
the mechanical, like the mechanical, structural mechanical, like intuition there. Yes.
Okay, thanks.
And so that's why if people, like if they do a quasi-statics calculation and they just can't get it to work, you often throw in a mass matrix, right? I don't know if who's ever done that.
Well, that's like the last ditch thing to do.
And the reason that you do that is because the mass matrix basically looks like the mass matrix that we have, and we know that it's symmetric positive definite. So it's well posed. And so if you add a mass matrix to an ill-posed stiffness matrix, usually you get a well-posed, what we call effective mass matrix out. So that's kind of a dirty trick, but that's what a lot of people do if you just can't deal with quasi-statics.
Better solution
Guilty.
to just get the boundary conditions.
Yeah, it is. That is a better solution. Yep. Okay. So let's turn the page now to a new topic. Let me go to the next guy here. Okay, so we just have been talking abstractly about bases, and basically the only concrete example I've given you so far is vectors in R2, R3, or Rn. Let's talk about other function spaces, in particular polynomial spaces, because those are dominant in numerical approximation. And there's a reason for that. There's a good historical and mathematical reason why polynomials dominate in the practical application of numerical methods. There's a sequence of very famous theorems from the early 20th century. The most famous is called the Stone-Weierstrass theorem, that established that for any continuous function on a closed interval, you can approximate it arbitrarily well with polynomials. And so this was a really important result that related this idea of just continuous functions, like functions C, we're using, this notation here, right? So all of a sudden you have these CK spaces, any function in here can be approximated arbitrarily well with some sequence of polynomial spaces of some degree, let's say, okay? And that kind of kicked off what we know today as kind of like classical numerical analysis, where you're basically doing everything with polynomials. All the approximation that you do is in the context of polynomials. And so the idea of polynomial bases is very important, because the quality of the approximation that you can do in a finite dimensional space will depend on the fact that you're using polynomials themselves and also the basis that you choose for that polynomial space. So I just wanted to expose you to some of the dominant guys. There really shouldn't be a prejudice with regards to different polynomial spaces. They all have different uses. So they all have pluses and minuses, and we use them basically interchangeably. And you use the basis that's most appropriate for the algorithm that you are working with at the time. And so it's good to be aware of all the different options. We can move seamlessly between all the different polynomial spaces using usually closed form change of basis operations. And so let's talk about them. So the most, I would say, well known is called the power basis. And it is simply a sequence of monomials, xi, so you have 1, x, x squared, and so on. This is a basis for the space of polynomials. Let's say we go up to x sub p. So it's a basis for p. I think the notation I used was to the p power. So polynomial space of degree p. Maybe we use degree 2 of these guys. But this is a very instructive basis to look at, because you'll notice that for those of you who are using finite elements, we never use the power basis for anything. So let's take a look at this basis more carefully. Can somebody just reason by just looking at that picture of an increasingly higher degree power basis where it's quadratic on the left, and we moved up to fourth order power basis on the right, what's a cause for concern? Just looking at the shape of the functions.
Well, I guess you can't represent anything higher than a certain order. That
Oh,
can-
yeah. Okay. Yeah, sure. That's a good point, James. I mean, you're limited by your degree, but let's assume that we've picked a degree that we want and we write down the basis functions. Even within those functions, there's a problem. Like in these pictures, you should see there's a problem emerging as we move from left to right. And I want, and it, visually, it's right there in front of your eyes. I just want to see if anybody can pick up on what the problem is.
Slope
Is it
is
the
converging to a steeper and steeper slope.
Okay, so that's an interesting problem. So the derivatives are becoming larger and larger.
I think also we
Um,
can point out that every other function is odd, and so it's going from negative to positive.
Okay, that may be an issue. So those are all good observations. They're not the dominant observation, though.
Well, these
Anybody?
ones can't capture a fourth quadrant.
Oh, down here, you mean? Oh, you can just take the negatives, multiply them by negative numbers to get down here. Yeah, so you can do that.
So
Okay, guess one last chance here.
I'm having
Just
a hard time.
visually-
You go ahead, Ryan.
Sorry, yeah, just like you can't even visually distinguish like x to the fourth versus like x to the sixth, you know? Like, I mean, unless they're like right next to each other and you zoom in, you're not going to be able to tell the difference.
Yeah, I mean, look what's happening to these functions. Like even this is x cubed here, this red guy. This is x to the fourth. What happens is, as that you go higher and higher degree, they become almost imperceptibly different. What does that mean? Like if you had two vectors, let's say here you have vector 1, and then you had vector 2, and I asked you, is this a basis for R2? What would you say?
Technically.
Well, I mean,
Within some error.
they're on top of each other, let's say. They're collinear.
Yes.
In other words, these two vectors are linearly dependent because one's on top of the other. Same thing here with the polynomials. Look, as the degree goes up, they become more and more similar, which means they become closer and closer to being linearly dependent upon each other. And so this is a big problem where for high degree power basis, analytically, it's a basis for the polynomials, but you have functions now that like basically are different by like some epsilon that's tiny. And so numerically, you're approaching more and more, you're getting closer and closer to a linear dependency in your basis, which means, as we'll talk about later, your operator becomes worse and worse, the more and more ill-conditioned, we say. Okay, and so the power basis analytically is a basis, it's fine, but numerically it's bad because the shape of the functions isn't good. They're close to each other in shape, which means that when you use them in a finite precision setting, you're going to get operators that are very poorly conditioned. Okay. So what we're going to do is let's do a change of basis. Let's find another basis for this same space of polynomials that doesn't have this property. And that's led to a lot of different classes. So let's take a look at what are called orthogonal polynomials. Okay. So the orthogonal polynomial, was there a question?
Yeah. This little boy needs to fall asleep, but he's struggling. Can you see that?
Yeah.
Okay, so the orthogonal polynomials, there's a few of them. I'm going to talk about the Legendre and the Chebyshev bases. There are others. They come from taking the power basis and orthogonalizing the power basis with respect to some inner product gives the different orthogonal polynomial bases. Okay, so what we're going to do is we're going to use a procedure which I haven't talked about yet. It's called the Gram-Schmidt orthogonalization process. we're going to apply it to the power basis with respect to some inner product. And the properties of the inner product will dictate the structure of the resulting orthogonal bases. So the Legendre basis is the basis that comes from applying Gram-Schmidt to the power basis with respect to a standard L2 inner product over the domain -1 to 1. Okay, so this inner product, if you orthogonalize the power basis with respect to this inner product, you get the famous Legendre polynomials. And they're orthogonal, which means that if you take any two of them, right, M, PM, and PN, and you integrate them according to the L2 inner product, it gives you basically a diagonal matrix with some scaling. Okay, so they're orthogonal. And these guys are very important in the theory of approximation of functions. If the quadrature that you guys have been reading about that we're going to be using, we call it Gauss quadrature, but really it's more properly Gauss-Legendre quadrature. And the points that you use, your integration points, are actually the zeros of the Legendre polynomials. So you can show that those zeros, if you use those as the sample points, you get good approximation properties. And so you can see that Gauss quadrature, just if you need any more convincing about how important these bases are and how much they've permeated everything we do, Gauss quadrature or Gauss-Legendre quadrature is nothing more than projection of integrands into Legendre polynomials. Okay, and so that's really what Gauss quadrature is doing, is it's taking sample points at the zeros of Legendre polynomials and performing a projection, a best fit of the integrand with respect to the Legendre basis. And so you look at Gauss quadrature and you'd have no idea that that's what's going on unless you kind of lifted up the hood and looked at the machinery. Okay, so let me now switch gears. I want to talk about the Gram-Schmidt process because it's very important all by itself. So we've alluded to the fact that you can take objects and apply this algorithm and get orthogonal objects. In fact, it's a general result. So let me go to where I've got this. Well, actually, it's the end of class, isn't it? So what I'll do is let's stop here because this is a good stopping point. Next time we'll talk about Gram-Schmidt, which is like the granddaddy of all orthogonalization algorithms. So QR methods, let's see, QR, this other one's escaping me, but all the kind of the classical ones you see in linear algebra, they're all basically different forms of the Gram-Schmidt process. And so we'll use this for all kinds of things moving forward. So we'll spend some time on Gram-Schmidt, and then I'll finish going from Chebyshev, Lagrange, and then we'll talk about the Bernstein basis. And then we will jump into some mechanics and the actual true finite element method. Okay, thanks everybody. Thanks for your attention. I'll see you in a few days.
Thank you.
Thank you.
All right, thanks.
Thank you.
Thanks.